In this section, we're going to talk about the chain rule. So first, let's review from our algebra classes what it means to have a composition of functions. So if you had this f of g of x, you read it f of g of x. What that means is we plugged x into g of x, and then we plug g of x into f of x. Or you plug g of x and f of x wherever you see an x. So how does that work? So let's say f of x equals x cubed, and g of x equals 2x minus 4. Let's find f of g of x. So that means let's put the g of x into f of x. So f of g of x would be equal to, so in f of x we have this x cubed, so instead of an x we're going to put everything in g. So we're going to put this 2x minus 4 where we saw an x cubed here. So you take this 2x minus 4 and you plug it in right here where you see an x. So you get 2x minus 4 all to the power of 3. And sometimes you might want to go the opposite way, so you might have something that was already a composition and you might want to decompose it into simpler functions. So you might get something like this h of x function, okay, and I look at it and I'm like, oh wait, this is a 5x minus 2 and this is a 5x minus 2. So they're kind of using the same thing there twice. That seems like might be a useful decomposition. So I might say, okay, well if I pulled that out, if I pulled those out and put in, say, like an x, what would I have left? So instead of all of that, if I just put an x, I'd have x squared minus 1 over the square root of x. So that would kind of be my outside function, if you will. And so my outside function, let's say that's f of x. And your inside function is kind of the part that you pulled out, or the 5x minus 2. And so that's how I would decompose it. Now let's just double check that that would have given us back what we wanted. So if you were going to do the composition again, you take this 5x minus 2 and put in where you see an x. So you put it in right here, so you'd have 5x minus 2 squared, yep, minus 1 over square root of x, so 1 over square root of 5x minus 2, yep. So I've decomposed it successfully. And so if those are my two functions, then I could say that h of x is equal to f of g of x. So we put g of x into f of x and we get what we started with. So this is the chain rule. This is when you're given, it asks you to find the derivative, but you're given it in two different functions. Okay, and so if you are asked to find the derivative of f of g of x, okay, it's two terms. Okay, the first one is f prime, but instead of x, you have to do f prime of g of x. So you put a g of x wherever you would have seen an x in f prime. Okay, which may not make sense at this point. We'll try it out. And then you times it by g prime of x. So here's what I mean. So they give us f of x and they give us g of x. We want to find the derivative of f of g of x. So what we're saying is we actually kind of want to do the composition. So we want to plug all of this in everywhere here. But instead of us actually doing it and then finding the derivative, we could just start from here and find the derivative. So what you do is you write out f of x and g of x. Oh, we've already done that. And then you take the derivative of each. So the derivative of f of x is 3x squared. The derivative of g of x would just be 2. Okay. But look at our formula. We don't have just an f prime of x. We have f prime of g of x. So then we have to plug g of x into f prime of x. So that gives me f prime of g of x. So I plug it in to my derivative. So take g of x and plug it into your derivative here. So you have 3 times 2x minus 4 squared times the derivative of g prime, or the derivative of g prime, which is 2. Okay, so this is my f prime of g of x. Oh, oops, times 2. I did that too soon. Excuse me, forgive me. Okay, so f prime of g of x was this piece right there. Okay, so now come back up and look at your formula. So now we can say the derivative of the f of g of x is equal to f prime of g of x. We figured out what that is. So you'll always kind of want to do this in multiple steps by writing everything out very carefully like this. Times, and then it said g prime of x, which we found out is 2. And so that's the derivative of what you would have gotten if you'd done the actual composition first. But this kind of saves us the step of actually having to do the composition first. You can skip straight ahead to the derivative of the composition. So let's try this next one. F of x equals square root of x, g of x equals 6x squared minus 3x plus 7. We want to find the derivative of f of g of x. Okay, so again we have to use that chain rule. So you start by finding the derivative of each one. So derivative of f prime of x. Square root of x is really x to the 1/2 power. I don't want to write it there. Let's see. So square root of x equals x to the 1/2. So if you take that derivative, you bring down the 1/2, and then you drop the 1/2 by 1. So 1/2 x to the negative 1/2, or 1/2 square root of x. Okay, and g prime of x would be, well, let's see, 12x minus 3. Okay, so we found f prime of x, we found g prime of x, and then you know if you're trying to do this chain rule, the derivative of the composition, you need to find f prime of g of x. So that means plug g of x into your derivative. So here's my g of x. And so I'm going to take my derivative, which is 1/2 square root, and then this x is where I put in my g of x. 6x squared minus 3x plus 7. So I found my pieces. You have to find 1, 2, well, that's kind of an intermediate. But you find 1, 2, and then 3 pieces. Once you've done all that, you're ready to use the formula. So the derivative of f of g of x is equal to f prime, evaluated at g of x, times g prime of x. Okay, so let's plug all that in. So f prime of g of x is 1/2 square roots of 6x squared minus 3x plus 7, times g prime, which right here we said is 12x minus 3. So again, this kind of seems complicated, but this is when they give us our two separate functions, and we kind of skip straight ahead to the derivative of the composition. Okay, sometimes, though, they present us with our original problem written in what seems like a different way. So you might get a situation like y equals u to the 5th minus 6u. And then u is actually equal to 3x squared. And so you kind of have these nested variables. So u is really a function of x and y is a function of u. But if y is a function of u and u is a function of x, really y is some function of x. We just don't really know what it is yet. And so what you can do is you can write the chain rule like this. So if you want to find the derivative of y with respect to x. Now if you just looked at y, how could you find the derivative of y with respect to x? There's no x's in it. But u is a function of x. And so what we can do is we find the derivative of y with respect to u. So that means find the derivative of this one times the derivative of the u one. And it ends up working out. So let's see how we'd actually use this. And again, we're doing 3 different ways to use the chain rule. It all comes back to the same theory. It's just 3 different ways that we can write it out. Let's see. Oh, and I want to point out, notice, as you look at this, dy over dx is equal to dy over du times du over dx. Now, technically, these aren't numbers, they're operators, but you could think of it as, hey, if I cancel the du and du, I just get dy over dx. So it kind of helps you remember what you're trying to do and make sure you get it in the right order. So if y equals u to the 5th minus 6u, u equals 3x squared, let's find dy dx. Okay, so first, let's find the derivative of each one. So the derivative of y has u's in it, so let's find the derivative of y with respect to u. And that's just find the derivative exactly like normal. So bring down the 5, u to the 4th, minus 6. Okay, now let's find the derivative of u with respect to x. So really, it just means come to your two equations and find both derivatives exactly like you normally would. Okay, so this is derivative of y with respect to u because we have u's. This is derivative of u because it's a u with respect to x because the variable is x's. So that would be 3 times 2x or 6x. So now dy dx is equal to dy du times du dx. Let's see, so then we have 5u minus 6 times 6x. Now technically you could stop here and you would be correct. But people might look at this and they might be like, okay, wait, why do you have 2 different variables? You have u's and x's. That doesn't really make a lot of sense. So what you can do is you can say, wait, this is a u, but we know that u equals 3x squared. So how about we just rewrite this and put that 3x squared into the u. So 5 times 3x squared minus 6, and all of that times 6x. And again, you should simplify these, but I'm not going to do that in the video at the same time. So this might have looked different than what we did up above, but it's actually exactly the same thing because we took the derivative of each one separately and normally, and then we took the g of x, or the inside function, and plugged it into the derivative. So we took each derivative like normal, but we have to plug in that inside function, that g of x, or in this case it was the u equals 3x squared, into our derivative for f of x, and then we multiplied. So it's exactly the same, just a different way to write it. We like writing it this way though for applications. It's much easier for applications. So let's see, a store sells shirts for $15 a piece. Let x be the number of shirts sold a day. Okay, R is going to be our revenue received from the sale of x, shirts. I'm not sure what that says, times. And what would be a good equation for revenue? So I would say, okay, revenue, if each shirt is $15, then revenue would be 15 times x, right? $15 per shirt, 15x. Now let's suppose that sales are rising at a rate of 2 shirts a day. Now if you're talking about rates, that sounds like something that would be a derivative. Okay. So let's see, our sales are rising at a rate of 2 shirts a day. Now sales is how many you sell. So sales would just be x. So this is telling us x is changing, and it's per day. So changing with respect to time. Okay. Or it would be telling us that dx dt. So the way I write this is I say, okay, x is the one changing, and t is my variable that it's changing with respect to. And so it's changing at a rate of 2 shirts. So it's 2 shirts per day. So that's how fast x is changing. Okay, and then my question is, how fast is the revenue rising per day? So here it actually told me how fast x is changing. But we really want to know how fast is the revenue changing. So let's try and find out what is dr, and it's revenue rising per day. So we want to find out how fast is the revenue changing with respect to time. So that's what we need to find out. Notice here that this is dr dt. It didn't say how fast is revenue rising per sale. It said per day. So we have dr dt, but over here we have a dx dt, and r is actually a function of x. So what we could say is, well, we could use the chain rule. And you have to kind of think about this one a little bit. You're like, okay, I want to end up at dr dt, so I'd probably start with the dr on top and a dt on the other one. Or you can think about it as, over here I have a dx dt, so I might want to use that, and this would then be dr dx. Or you think about it as r is a function of x, so if I try and take the derivative of r, I'd end up with dr dx. And then over here I have the dx dt. But you should make sure when you're done that the dx is canceled and you'd be left with dr over dt, which is what you wanted. Let's see, so we need to know dr dx. We also need to know dx dt. Come over here. Oh, dx dt. I know that already. Let's just go find dr dx. Well, if r equals 15 times x, then dr dx, if you just take that derivative like normal, it would just be 15. So coming back here, dr dx, well, we found that, that's 15. dx dt, we found that, that's just 2, so 30. So revenue goes up $30 a day. Which actually makes sense because this was a very simple problem. If each shirt gives you $15 and you sell 2 more shirts, your revenue should go up $30 more. Okay, so again, you have to use a chain rule. You look at r and say, if I took the derivative of that, I would just get dr dx. But I really want a dr dt, and so you have to use that chain rule. Let's try this one. The demand equation for an MP3 player is P equals 24 minus 0.003x. So P would be the price of one calculator in dollars. Okay, or it's the maximum price you can charge to make sure you sell X MP3 players. Oh, sorry, this is supposed to be MP3 players. So P is the price, X is the number of players. Right now, our company makes and sells 400 MP3 players a day. If the company decides to increase production by 50 players per day, how fast will the revenue increase? Okay, so let's go through. Let's see. Company decides to increase production. Production is X. So X changes at 50 per day. And we want to know, so how fast is revenue increasing per day? Okay, so if X changes at 50 a day, that's telling you X is changing with respect to time. So that's a dx dt is 50. And we are trying to find revenue. So we're trying to find dr dt. Now to find dr dt, okay, we know we're going to have to use a chain rule because that's what section we're in. Okay, we say I know a dx dt, so I'm probably going to want to use that. Okay. So what needs to go here so that we'll cancel and get to dr dt? Well, I would need a dr and a dx. It also makes sense because if we want to find the derivative of r, somehow we're going to need an equation of r. So let's find an equation of r. They didn't actually tell me my equation for r, but they did tell me an equation for p. And r is also just known as x times p, the number you sell times the price you sell each one for. So in our case, it'd be x times 24 minus 0.003x. So our revenue is a function of x. So if I take the derivative of my revenue, I would get dr dx. And so that's kind of how I know what needs to go there. So let's actually look at this. Let's simplify that a little bit. So x times 24, so 24x minus 0.003x squared. So let's take the derivative of that with respect to x because that's the variable in there. So derivative of 24x would be 24. Let's see, minus 0.006x. Now notice, this still has a variable in it. And if I try and plug in here, I'm going to get variable in my answer. I want to have an actual number. So what we need to do is we need to figure out, well, what should x be? So coming back up, it tells us, oh, our company makes and sells 400 MP3 players a day. So x is 400. So let's plug in 400 here. So what I can do to write this is I say this is the derivative of my revenue and I evaluate it at x equals 400. So that little vertical line means evaluate it or plug in x equals 400. So that would be 24 minus 0.006 times 400 is 21.6. So my revenue is changing at a rate of 21.6 per MP3 player because this is with respect to x. So now you come back up here though because this is what I actually wanted to find. So I found the derivative of r, but it had to be with respect to x. But I really want to know how it changes with respect to time. So I'm going to times it by dx dt. So dr dx is 21.6 and dx dt is 50. So it's going to change at a rate of $1,080 per day. So if you increase by 50 more MP3 players a day, your revenue will go up by $1,080 per day. Now all of these will kind of take some practice. It's a different way to look at the chain rule. My next way though that we're going to look at the chain rule is one that you've actually already done, so it is not new at all. Okay, and so this is, we'll use this chain rule if we just have one big complicated function. Okay, and it's just, remember our old general power rule where you just do derivative of outside times derivative of inside with all the boxes? Okay, super simple to me. This is the much easier way to do it, and it's what you'll actually be using the rest of the semester. So in this section, you'll do a few where it's the individual functions, but then from then on out, you'll just use this normal chain rule. To me, it's easy. It's not one I have to think about really hard. Okay, so when you look at it, you try and figure out, okay, well, what would be my inside? What would be my outside? Where do I put the box? So I put the box around the stuff inside the square root. So then it's like the square root of a box, or whatever's inside the box to the power of 1/2. Okay, so derivative of outside, you should say, okay, when you take the derivative of something to the power of 1/2, it's 1/2, keep your box the same and drop your power by 1, times, now take the derivative of what's inside the box. So inside the box is 3 times this 5x to the power of 4. And inside the box, you keep it exactly the same. So again, this is doing exactly what that complicated looking formula for the chain rule did. It's just a lot easier than actually thinking about it. And you're done. You can go ahead and simplify on your own. Okay, so again, this was derivative of the outside. This was derivative of the inside. Notice, once again, we didn't actually have to learn anything new. You've been doing this for several sections. Okay, let's try next one. If w equals 5x squared minus 2 to the power of 7, let's find the derivative of w with respect to x, and we'll evaluate it or plug in x equals 3. But we'll worry about that part at the very end. Let's just now find the derivative of w with respect to x. Okay, notice, let's come through here. Let's put our box around 5x minus 2. So I have a box to the power of 7, basically. It's my outside function. So this derivative is you bring down the 7. You keep the box exactly the same. So the stuff inside the box stays the same. And you drop your power by 1. Times, now you do the derivative of what's inside the box. So inside the box, the derivative of that would just be 5. So derivative of the outside, derivative of the inside of the box. So in our case, we have 35 times 5x minus 2 to the power of 6. Now, if you want to plug in, so this line means plug in x equals 3. So if we take the derivative and we plug in x equals 3, we're going to get 35 times 5 times 3 minus 2 to the power of 6. And you can put it into your calculator to find that it's 8.87 times 10 to the power of 15. So again, derivative of the outside of the box times derivative of the inside of the box. No complicated looking formulas. And example 11, if h of x equals, now notice this one looks pretty complicated, 5x minus 2 to the power of 2 minus 1 over the square root of 5x minus 2. This is a little bit more complicated than anything we've done with our boxes yet, but I think we can still do it. So I notice again that this would kind of look like an inside, and this would also kind of look like an inside. So I would say that this was really a box squared minus 1 over the square root of the same box. Or box squared minus, let's see, if it's over the square root, this was x, not x, box to the power of negative 1/2. So we'll just rewrite that. So inside our box we have 5x minus 2, and then this is kind of the outside of our box, the outside function. So let's take our derivative. So you take the derivative of the outside first, so you bring down the 2 times the box to the power of 1 minus, bring down your negative 1/2 power, box, and drop your power by 1, so negative 3/2. And inside the box, you put 5x minus 2 again. Okay, so that's the derivative of the outside of the box, times now the derivative of the inside of the box. The derivative of 5x minus 2 is just 5. So this entire thing was derivative of the outside. This is derivative of the inside. Let's see. So this is going to be 5 times 2 times 5x minus 2 minus a negative is plus. That negative exponent means take it down in the bottom, so 5x minus 2 to the power of 3/2.